let's get into it. And up front, I wanted to apologize if I come off as distraught and upset. I'm going through a bit of a hard time right now. I missed F1 qualifying today, so it hurts. So today I want to talk about programming languages and like what better of a conference to do that at one that describes itself as a polyglot conference. But first, who am I? Obviously, I am Dillon Mulroy. I am a software engineer at Raleigh. I've been a software engineer for going into 11 years now, with the majority of my experience being in TypeScript, Node, and React. Been writing React since the days of class components and mixins. I do a lot of Twitch streaming. I stream programming content Monday through Friday, 7 a.m. to 10 a.m. Eastern time, so if that's your thing, check it out. You can find me yapping and shitposting on Twitter, and you can find some of my open source work at my GitHub. And then you can find all these links at my personal website, which is dillonis.online. Unlike everyone else, I'm going to force you to go to this link and take a screenshot. But really, there's going to be a lot of code in this talk. And if you want to follow along on your personal device, feel free to go to my GitHub there. My slides are in a PDF. OK, so back to programming languages. So the heart of this talk has really revolved around my journey in programming languages and my kind of journey in determining like what features I have found working across multiple languages, multiple paradigms, multiple stacks that I feel are conducive to building quality software, building reliable software, building software that not only scales on a technical level, but more importantly, scales on like a human organization and process level. So let's dive in. So as far as programming languages, we've really never had it better or had more choices. We are kind of living in the era, the golden era of programming languages. I mean, across the past 2 days, we've had talks on Dart, Flutter, TypeScript, Python, everything, right? There's a ton of choices to be had out there, and each brings its own unique qualities and benefits to the table. New languages are taking the best features and ideas from those that came before them, and adding features and capabilities from cutting-edge, modern PhD programming language research. In addition, older languages are evolving and modernizing to add these capabilities as well. The Perl talk earlier is a prime example of this. Perl is actually catching up with a ton of modern languages with a bunch of modern features. Look at Java. If you compare Java 1.6 to what are we at, like 1.20 nowadays, there's a ton of nice modern features in the language now. So what are some of these features and capabilities that I'm talking about? Things that we're starting to see emerge or that we're starting to expect in our new languages and our runtimes. Well, up first is linear types. And if you're unfamiliar with linear types, they are what power Rust, and more specifically, Rust's borrow checker and lifetimes. In addition, Chris Lattner, who is the creator of Swift and also LLVM, he's creating a new language called Mojo, which is a superset of Python, which also uses linear types and can get to the performance of Rust. Things like algebraic effects. Diving into what algebraic effects are is a little bit beyond this talk, but there are languages experimenting with this. Languages like Coca. OCaml recently added algebraic effects to the language, which powers its multi-core capabilities. And if you're a React developer, how many React developers in here? Hands up. Quite a few. Are any of you familiar with suspense and how suspense works? Suspense is pretty much a poor man's implementation of algebraic effects. Under the covers, what's happening is the runtime is throwing a promise, and your suspense boundary is catching that promise, and it will resume the operation from lower down in the child hierarchy when that promise resolves. So gradual type systems, right? Look at TypeScript as the prime example of this. JavaScript, 10 years ago, everyone was writing plain JS. Nowadays, TypeScript is ubiquitous. They added types to the language, and you'd pretty much be crazy to start a project and not use types. Likewise with Elixir. Elixir is working on adding set theoretic types to the language, which is also super cool, and I could give a whole talk on that. Next year? Yeah, sign me up. Then we have things like algebraic data types, and more specifically sum types, which you can think of as kind of like enums on steroids. And then pattern matching, which if you've never worked in a language with pattern matching, once you do, it's really, really hard to go back. Immutable and persistent data structures. A prime example of this are the data structures that power Clojure. Basically, you can act on data structures in an immutable way, and it does deep structural sharing, so you don't pay the cost of doing tons of allocations and copies. And then actor-based concurrency models with Elixir, Erlang, implementations in Scala and Java with the Akka framework. We see this popping up more and more. So we've never had it better or had more choices. Choices. So many choices. How do we decide, right? We have TypeScript, Go, Java, Elixir, Haskell, PHP, Swift, Rust, Kotlin, Ruby, Python, Rock, Zig, OCaml, Dart, C, C++, C#, F#. The amount of choices is dizzying. How do we make sense of all of these different languages and their particularities and their runtimes and the features they offer? Well, in particular, I want to share my journey in programming languages, and more specific, give y'all a timeline of my professional career and the takeaways that I've had working in these languages. Now, I've been very privileged to be able to have worked in such a high variety of languages across my career. So let's dive in here. So my first job was in 2014, and I was working full-time at State Farm. The first team I got put on, I was writing in Java 1.5 and using struts. If you don't know what struts is, you're better off for it. My main takeaway from my time working in Java, I did eventually get onto a more modern version, Java 1.8, and I got to use Spring Boot and all the niceties that come there. But regardless, my takeaways remain the same. On the positive side, I learned about the value of a mature ecosystem. Like, you got Jota Time, you have Spring Boot, you have all these things not necessarily out of the box in the standard library, but like de facto standards for building applications in Java, right? On the downside, I learned that I really, really dislike syntax for the sake of syntax. Java is super verbose. It's making strides in this department in newer versions of the language, but regardless, it is still verbose. I also learned that dev tooling can make all the difference in the world. As powerful and good as Maven and Gradle are, they are a pain in the ass to work with. So from Java, I kind of transitioned into JavaScript. And like up front, my mind was blown, right? My background is working in Java. And I get to step into this world of a dynamically typed language. And I'm like, whoa, this is so nice. I don't have to deal with all the dogma of the Gang of Four book and design patterns and over abstraction and blah, blah, blah. I can just write my code, I can write functions and be on my way and be super productive. At the same time, this was probably like around 2014 as well. We were getting like good tooling, like Webpack was coming onto the scene, Browserify at the time, NPM was growing. So seeing these modern tools that were effectively, in my mind at the time, doing similar things as Maven and Gradle, but it had just had a such better experience. It was so easy to use. I could just do npm install, get what I needed, and go on my way. So next up, I got to work on a small Elixir project for 6 to 8 months, and this is where I got my first taste of functional programming. And I really didn't understand what that meant at the time. But I think the bigger takeaway that I learned from Elixir is the power of having good concurrency primitives in a language. Concurrency in Java is kind of a pain. I think it's got green threads now, I'm not sure. But using the actor model in Elixir made it so incredibly to scale. I was responsible for building this little microservice that sat in front of a suite of front ends that was effectively acted as a cache for a particular kind of data, and on a cache miss, it would fan out, query like 8 different databases, join that back together, put it in Redis, and feed that back out to these clients. And like the ease of doing something like that in Elixir is just, it's unbelievable. Next up, I got to work in Go. And this is the first statically typed language that I used outside of TypeScript, or not TypeScript, excuse me, Java. And like up until this point, my perception of what it meant to be a statically typed language or for a language to have types was like just Java. I thought that's what types were. Any language that has types, it's gonna look and feel like Java. Go uses duck typing and structural typing, and it does it in such a way that it uses minimal syntax to do it. So the two really positive things that I took away from Go is that having a small, simple, and opinionated language is a really beneficial thing. You can drop most engineers that have a little bit of experience into a Go code base, even if they haven't written Go, and they can probably be productive within a day or two. That makes it quality. The other big takeaway from Go, it was the first time I had experienced really treating errors as values. And some people like to, yap on Twitter about, if nil or if error equals nil over and over and over again. But to this day, the services I built in Go are probably some of the most resilient services I've ever built. Like I was confident in how they were gonna run, how they would crash, what they do when they crashed. Like I don't think I ever once got paged for the Go services going down overnight. And also, again, another language with amazing concurrency primitives baked into the language. So then move to TypeScript. I had obviously got a taste of what types were like in a good language like Go. And up until this point, I was super apprehensive about adopting TypeScript. This is probably, I started using TypeScript somewhere between 2017 and 2018, and at the time we had like Flow competing and some like ReasonML people coming in talking about ReasonML. It's like, what do you choose? And I kind of got the benefit of waiting that out till it was pretty clear that TypeScript was going to be the winner. At this point, I had moved to a company called Formidable, which back in like the 2016 to 2021 era, they were relatively popular in the JS open source community. A couple members of the React Native team worked there. A bunch of GraphQL like OGs were there as well. So that was an amazing place to like cut my teeth and essentially become a very deep expert in JavaScript, TypeScript, React, Node. It really also taught me, it solidified my appreciation for types, right? TypeScript's type system, not the best in the world, but worlds better than just plain JavaScript. Consistently, I was, as a consultant, I was dropped into dozens of companies ranging from small startups to Fortune 500s to FANGs. And seeing just the value that types can bring to like the integrity and the reliability of your applications was emphasized over and over and over and over again, seeing it work across clients. Next up is Lua. I use NeoVim, by the way. So yeah, we see some nods back there, let's go. So I maintain two relatively popular NeoVim plugins, specifically working with TypeScript. But Lua was, again, a really good reminder of that a simple, small, and opinionated language can make you super productive super quickly. Like Lua is a very tiny language, not a lot of features. They use the same data structure for hash maps, lists, and everything in between. It's literally just called a table. So yeah, that just grew my appreciation for being simple. Next up, I took a job at, I see Vlad clapping his hands together. I took a job at a startup where effectively, well, I was hired to lead the front end team, which was all TypeScript and React. And I've been a full stack career genuinely my whole career. I've worked both sides of the stack at every single job I've ever held. And if I wanted to contribute at this company in a full stack way, it necessitated learning OCaml. This company, all of the backend services were in OCaml. We had an Excel plugin built in OCaml. Our admin app was a OCaml code base that compiled to JavaScript. And to be quite frank, OCaml was probably the most valuable experience learning-wise in my career. It fundamentally changed the way I approach problems, the way I think about problems, how I, between TypeScript and OCaml, I have adopted a pattern of thinking and approaching problems at the type level prior to writing any code. I think about these problems in types. It also really solidified my appreciation for errors as values. OCaml famously uses the result type, options as we learned about earlier. I cannot express my appreciation for having had that opportunity enough. And finally, over the past 6 months, I've been learning Rust. And I think I've found the experience of writing Rust a little bit easier than most people. And I've never written a lick of C or C++ really in my life. Rust was originally written by OCaml devs. The original Rust compiler was written in OCaml. All the features people love in Rust are generally inspired by OCaml. So it was a pretty fluid transition to start being able to write Rust effectively. So where does that leave me? Well, quite frankly, I'm unsatisfied. There are so many languages that get close to being ideal, yet fall short, right? TypeScript, its type system is unsound, and we'll get into what that means in a little bit. Go, also an unsound type system, and you have things like an empty interface, which is effectively any. You can still get nil pointer exceptions. Rust is really hard to onboard new people to if they haven't had experiences in a language like OCaml or C or C++. Elixir, while getting better and getting set theoretic types, is still a dynamically typed language. All of these have features I love and have contributed in some way to how I build reliable software, at least what I consider reliable software, but yet none of them have everything I want. So what features would my ideal language have? Well, it would have a sound type system. And what a sound type system means is if your code compiles and type checks, it will not have a runtime type error. I would also prefer if my type system was based on Hindley-Milner. And Hindley-Milner is a type checking algorithm and type system found in languages like OCaml and Haskell. We'll dive into it a little bit more here in a moment, but I want my type system to work for me instead of against me. When I'm writing TypeScript, once you get past the top level and you get into the world of having to write deeply generic types and work with type mappers and union a bunch of types together, you get into these giant ternary trees trying to capture the dynamism of JavaScript, it becomes a burden. And it takes a long time to build the muscles to learn how to be productive and work through those problems. Additionally, and this is a benefit of Hindley-Milner type systems, is I want static typing safety, but I want dynamic typing simplicity and ergonomics. I want to be able to move fast and I want my types to help me, but I don't want my whole focus to be just battling the type system. So the way Hindley-Milner works at a high level is as you're writing code, let me back up a little bit. Hindley-Milner, you can get away with not annotating 95% of your types in your program, and it will 100% bulletproof infer the types. And this is not inference like you would see in TypeScript. TypeScript is gonna infer a structural shape of your data, where a Hindley-Milner system is gonna infer some nominal type that you've declared elsewhere, and it's gonna figure it out by usage. And the way it does that is when it's compiling your code, is it's gonna build up these equations of constraints, looking at how you're using expressions and how you're using variables, and it basically solves those equations and says, oh, I know that this value can only be this type user because it was used in such a way and it has this field. And also, and this is an experience if you've ever written Rust, if it compiles, it's gonna run. I also want simple polymorphism in generic programming. Also a nice trait found in this kind of a type system. And also, it also enables us to have some really nice compile time optimizations. The next thing I want is errors as values. I want to throw try-catch in the frickin' garbage. And a little hot take here, despite having built my career mostly in TypeScript, I have a pretty hot take on the language. So my hot take is that JavaScript has the lowest bar of entry to building and being productive, which is a good thing, but one of the highest bars of any language and stack to building high quality, stable, and reliable software. Very few devs have the expertise to pull off the ladder. At Vercel and Formidable, I've worked with some of the best JavaScript devs across the planet, and we still fall into these traps and mistakes because of the language and its runtime. And a lot of this is because of try-catch. If I could take one feature and add it to TypeScript, it would being able to annotate that a function throws, right? When you bring in a library from an NPM package, or maybe you're working in a giant repo with dozens of teams, you have no idea if a function throws or not. And JavaScript and TypeScript promote a style of programming where you focus on the happy path. It enables you to focus solely on the happy path, right? If you write some code that can throw an error, it's so easy to say, oh, well, I'm not gonna write the try-catch code here, my caller can deal with it. And then that bubbles up the stack to the top level of the application, and suddenly you're getting paged at 2 in the morning for an unhandled promise rejection. So what do I want out of errors as values? Well, ideally, I would like a composable type like the result type found in OCaml and Rust, but I would be equally as happy with a less ergonomic error type like Go uses. I also want the compiler and the LSP to enforce explicit handling of the unhappy path up front. I want to be able to strongly type my errors. I want to give context and meaning to my errors. I want to be able to let my callers decide how to handle the variety of errors my code can produce. Maybe, a file not found error isn't meaningful to the caller and they can just ignore it, or maybe that should crash the process. I want to avoid control flow interruptions. This is what try-catch is, right? You interrupt control flow, bubble up, collect the stack, so on and so forth. All of these together promotes more reliable, stable, and maintainable software. I also want sum types and pattern matching. As I described earlier, sum types are pretty much enums on steroids. And in fact, the sum types in Rust are literally called enums. Enums let us encode meaning along with our data. Sum types and pattern matching together let us express, model, and safely handle complex data structures and control flow with ease. It lets you be very declarative about the state of your application and the code paths it can follow. And we heard twice in this conference already from 2 different speakers the benefits of making illegal states unrepresentable at the type level. We want to guide our developers to doing the right thing and make doing the wrong thing as close to impossible as possible. And we also, with pattern matching, get exhaustive case analysis. So we actually do kind of have this feature in this TypeScript world, where if you switch on some value and you don't handle all of the cases, the compiler is going to yell at you and be like, hey man, you didn't handle XYZ cases. You need to either have a catch-all clause or handle these. I also want first-class concurrency, right? We've already talked about the value of having baked-in concurrency. Also, another reason that I have started to move away from using Node on the server. As soon as you get into wanting or needing to do concurrent things in JavaScript and Node and TypeScript, you have to solve that problem with infrastructure. Our last talk, literally talking about using temporal to solve these problems. I'd also like it to embrace the actor model. The actor model is just a really simple way to wrap your mind around handling concurrency, and it removes the need for a lot of complexity, which we'll cover in a second. I want to have lightweight, isolated units of computation, preferably actors, powered by green threads. So green threads are what power Erlang and Elixir's processes. It's what powers Go routines, Tokyo's tasks. And what green threads are essentially like 4 kilobyte size processes that is managed by a scheduler, a preemptive work stealing scheduler that lets you you can blast off millions of these things at one time and do it all concurrently. I also want simple cross-process and type-safe communication via message passing. I would like to have fault tolerance through supervision hierarchies. So I would like to be able to spin off these concurrent processes, and I would like the process that spawned them to dictate what should happen when a child process encounters an error. Should it just not spin up? Should it spin up n number of times? Should it retry? What is the interval it should retry? Should it always restart? I want to be able to easily scale from a single core on a CPU to fully distributed systems. And embracing a actor model reduces the need for low-level synchronization primitives such as mutexes, semaphores, and read-write locks. I also want a strong emphasis on DX. I want it to be a core value of the language I'm working in. I want it to be simple, friendly, and opinionated, right? These are the lessons I took away from writing in languages like Go and Lua. I want there to be like one obvious way to solve common problems. Like, don't make me go searching through the docs for how to use some syntax. Don't give me, this is kind of a problem in OCaml and even more in Haskell. You can solve problems dozens and dozens of ways, and you can get so caught up in building the abstraction, not so different than Java devs and C# devs, you know, building out the entire gang of for-book patterns. I want a unified and modern toolchain. I want package management, the build tool, formatting, documentation generation. I want that all in one binary. I don't want to have like 5 different tools to do all these things. I don't have to be updating my prettier or biome version all the time. I just want one version that's baked into the language. I want approachable, searchable, and thoughtful documentation. I think 2 languages in particular that get this really right is Elixir with hex docs and Rust with cargo docs. They're like top of the line. You can generate docs easily from cargo or from mix. It's just an amazing experience. I also want friendly and informative error messages. I think 2 languages that get this right are Elm. Has anyone written Elm in here? A couple. Elm, hands down, has the best error messages across any language ever. Rust adopts a similar style to Elm error messages, just a little bit more complex just due to the nature of the language. I want fast compilation times, and I want the language to favor backwards compatibility, and more specifically, language simplicity over excessive flexibility and features. Code once, run everywhere. I want a language, my ideal language, to embrace versatile compilation targets in runtime environments. I don't want to have to be switching from TypeScript to Go or to Rust. I just want to work in one language and be like an expert in that language, and I want it to be flexible. I want support for compilation to JavaScript so I can run it in the browser or on the edge, and I want to be able to easily bind to existing JavaScript packages. I want to be able to share my types across the front end and the back end. I would love to have support for serverless and edge environments. I also want simple cross-platform support. And a huge plus would be having native and WASM targets. So, as many of you are probably already aware of, I haven't been completely honest about my programming language journey. There is another language that I've been working with for roughly the past 7 months. That language is Gleam, your next favorite programming language. This is also Lucy, the official mascot of Gleam. As described on the Gleam website, Gleam is a friendly language for building type-safe systems that scale. Gleam is a sibling language to Elixir and Erlang that runs on the Beam, otherwise known as the Erlang VM. Gleam uses a simplified implementation of the type system found in Haskell and OCaml. But wait, there's more. Gleam can also compile to JavaScript along with generating TypeScript type definitions in the form of .d.ts files. Gleam also isn't exactly a new language. It's been in development since 2016. Louis Pilfold is the creator and maintainer of Gleam, and as you can see, they started in 2016 and then really ramped up over the past couple of years. And that has led ultimately to the 1.0 version release that Gleam is considered production ready and stable. That was released on March 4th. Also, I don't think GitHub stars are exactly the greatest way to gauge a project, but I think it does say something that Gleam is one of the fastest growing languages on GitHub as far as stars go this year. I mean, that's like straight up like exponential growth. So what does Gleam look like? I want to show you guys some real code that I've written for a tool called Glitch that I work on, which is pretty much just a Twitch SDK written in Gleam. So up first is a type that models Twitch's representation of a user. So we have this pub type user. Inside of it, we have a single constructor, and that is also called user. That's kind of a common convention. We call this a record type. But you can see we have an ID typed as a string along with login display name. We have this user type, which I should have used a better name than type, but that is another type declared somewhere else. That should be user type. We have a broadcaster type, also another type declared elsewhere in this module. Then we have description, another string, profile image URL, which is typed as a URI. And we have an email, which is an option of string, which we've had the pleasure of already learning about options in Lambda calculus earlier. And a created at timestamp, also modeled as a string. Now I want to talk about this option a little bit more. This is kind of the first view we have into polymorphism in Gleam, or generics. And what this looks like is Gleam does not have null or undefined, much like Rust, right? We model that kind of a value with an option. So here, this is the actual implementation of a option enum in Gleam. Like this is straight up out of the standard library. So an option is generic over some type A. You'll regularly see A used as like the first generic parameter in a lot of functional programming languages. Most devs, if you come from like C# or Java, this is the same thing as like using T as the first generic argument. So we're generic over some type A, and we have two constructors or variants. The first is sum, indicating the presence of some value of type A, or we have none, indicating that what would basically represent null or undefined. So here's some code for requesting users from the Twitch API. So we have this getUsers function that takes a client, a getUsers request, and we're going to return a result of a list of users or a Twitch error if it was unsuccessful. You see here we create a new Helix request. That's what they call their API. We set the query parameters and derive that from our request. We set the request path, and then we do this kind of strange looking line where we say use response result.try client.get. This just issues a get request to the API and like almost unwraps the value if it's successful, similar to like you would use await in JavaScript. It's not quite the same, but you can think of it unboxing a value similar like you would use await to unbox a promise. And then we use our API response module to convert that into list data. Now, I mentioned earlier that languages using Hindley-Milner can get away with not annotating the majority of your types. Now, I still like annotating types, especially at like top level API surface. I think it's just helpful for your coworkers, helpful for consumers, good for self-documentation. But we could equally remove all the types here, and this code's still going to compile and run because the type system can accurately infer those types. So here's another type. Again, an enum, and this is the kind of messages that the WebSocket API that you can connect to Twitch will give you. So you can get notifications, or session welcomes, session keep alive, session reconnect, or revocations. And I often will log these statuses to logs, and I need a way to convert these types, these enums, to strings for the logs. So we have this message type to string, takes a message type, returns a string. We pattern match on message type, and we handle each of the cases. If I didn't handle one of these, this is what I said earlier about exhaustive case analysis. If I didn't include session reconnect, the compiler is going to yell at me and not let me compile my code until I handle that case. And same as before, we can just completely forego the types here, and the compiler is going to accurately infer our types. So how would I describe Gleam? I like to describe Gleam as a language with the simplicity of Go, the type system of OCaml, the concurrency model of Elixir, and the syntax of Rust, just without the hard parts. But does it meet the requirements of my ideal language? Let's find out. First, a sound type system. I think y'all already know where I'm going with this. But let's dive into an example. So, as we've already covered, Gleam uses an implementation of Hindley-Milner. This means we have a sound type system with powerful type inference. As an example, you'll find commonly in languages that use Hindley-Milner is that you'll have specific operators for your different numeric types. So if you want to operate on floats, you have to use plus dot, star dot, slash dot. Got ahead of myself. We could also annotate this function, right? A is a float, B is a float, and we're going to return a float. If we remove the types and we were to look at what the compiler infers the type of this function to be, you'd find that it's inferred to be a function that takes two floats and returns a float. This might actually look pretty similar to some of the lambda calculus we were looking at earlier. Next up is add2. This one operates over ints instead of floats. We're using the normal plus operator. Again, the compiler is going to infer this as a function that takes two ints and returns an int. And finally, we have this function apply. We have an x, a y, and an apply function as arguments. We call apply on x and y. Can anybody guess what the actual inference of this type would be? Bueller? Bueller? Yeah. What is it? A. Where at? Which question mark would be A?
All of them.
All of them? Incorrect. Here, I'll give a hint to the audience here. The type definition for the apply function is a function that takes an A and B, some generic A, some generic B, and returns some generic C. So let's just put that in place up there. Correct. That's exactly what it is. It's a function that takes some generic A, some generic B, and then another function that receives the A and the B, returns a C, and then the outer function returns the C from the callback passed in. So if we look at how we would use apply, we can pass in 10.4 to add, and this is going to be inferred as a function that takes a float, another float, a function that takes a float and float, which returns a float, and then ultimately we return a float. And similarly, if we were to annotate our A variable here as a float, we're not going to get any sort of compiler error. Next, if we called the same function, again, a good example of parametric polymorphism or generic programming, this apply function can operate over really any type. So this is inferred, same as above, just with ints. So yes, Gleam has a fantastic, wildly friendly type system. Now, does it have errors as values? Well, yeah, we use the same result type found in languages like OCaml and Rust. And this is going to look super similar to our option type. And in fact, they're kind of isomorphic, right? Like an option is just kind of a result type where the error variant is none. So what this is saying here is that we have a result that is generic over some OK type and also generic over some error type. A OK operation is going to return an OK constructor that carries data along with it, and that data will be typed as whatever the OK type is, likewise with the error. So what does this look like in practice? Let's say we have some function to fetch data from like an endpoint, right? So we have this fetch data function. It's going to return some result type over a generic data type, and then it's going to return a request error. Again, we're not going to implement this, but we can see how this works out in practice. So if we were to look at the type of data, or what the compiler is inferring it as, it would be exactly as the return value is above, right? It's going to be result, some generic data, and then a request error. And now you may be saying, well, we can't really do anything with the result, right? Like, how can we get at that data? Like, we want the OK variant. And this is like a crystal clear example of like how languages like this force you to consider and handle the error path. We can't just go on our happy way and assume we have a OK here. Like, we have to make the explicit decision to handle this. And one of those, we have multiple ways we can handle result types. So the first one is we can use assert. And this is great for like prototyping or maybe some like bootstrap function where you're starting up your application. But what assert effectively does is it's gonna match on a pattern. And in this case, we're matching on, we wanna say if the return type of fetch data isn't okay, we want to pull that data type out of the constructor so we can use it elsewhere in our code. When you use let assert, if it doesn't match the pattern that follows it, it's going to panic and crash the current process you're in. So it's not that much better than using try catch. The next option we can do is we can just pattern match. So we can pattern match on fetch result, and we're going to have to handle both variants or constructors because of exhaustive case analysis. And we can match on the OK, we can pull the data out, process it, and then we also have to explicitly handle or ignore. We can choose to ignore errors, right? But you have to be explicit and intentional. And finally, well, actually not finally, we can also use the unwrap. And this is the unwrap, you might have seen this in Rust before. The unwrap in Gleam operates slightly different than the unwrap in Rust. Unwrap in Rust works similar to how the assert keyword we just looked at. If you unwrap a value or you unwrap a result in Rust and it's the error constructor, your program is going to panic. In Gleam's case, we provide a second argument, which is a default value. So what we're saying here is, let's try to unwrap our fetch result. And if it is the error constructor, we're going to return boom as our value, and that will be assigned to data. And then we can process that. And the final way is using the use keyword. As I said earlier, you can kind of treat it with the same mental model as like await. If you're familiar with Rust, this is going to work a lot like the question mark operator. What this effectively does is says, hey, I have like this box type, and I want to try to pull the value out. So if it's the OK constructor, it's just going to assign it to the variable data. But if it's the error variant, we're going to immediately return from the current scope with the error value. So if it's an error, it's just going to immediately return from this function with the error. So yes, we have errors as values and with our composable result type. So next up is sum types and pattern matching, which we've already seen in practice. So I assume you guys see where this is going again. So to really display how sum types and pattern matching work from like a first, I don't even know what the expression I'm going for here is, but like from a foundational level, let's implement rock, paper, scissors. So up front, we're going to need a type, an enum type or a sum type to represent a move, right? So you can throw a rock, you can throw paper, or you can throw scissors. We also want to be able to represent a game result. And this is kind of like what I was saying earlier, where we can provide meaning and context to our data through the type system. So our game result has 3 different variants or constructors. Player 1 wins, and that carries 2 pieces of data with it, through, meaning the move that player 1 threw to win, and the move they beat from player 2. Basically the same thing for player 2, and then we also have draw, which just carries the move that both players threw. Next, we want a way to log out the move to standard out, so we're just going to write a quick little toString function that takes a move, we're going to match on it, and basically just convert it to a string. So next up, this is pretty terse. I had to remove some parentheses to fit this code on a slide, so we're going to break this down a little bit here. So if we focus just on this first arm of our pattern match, we're matching on a game result, and if it's the player 1 wins constructor, we're going to pull out the move they threw and pull out the move they beat. And we're going to say player 1 won by throwing, convert through to a string against doing the same thing for the move they beat. Likewise, we do the same thing for player 2, except we change that to first string where it's player 2 won by throwing. And finally, we handle draw, where we just take the move that both players threw and log out draw both players through, convert that to a string. So you can kind of see like how we're able to like declaratively map all the possible edge cases and code paths in our code in like this really distinct way that you can quickly scan and see like all the possible routes your code can take. I know this is like kind of verbose here, and the next example is just as verbose, but it is actually less code than if you wrote the same logic out in a large if then else statement. So looking at the actual game to run the function, let's narrow in on line by line. So we're going to pattern match on 2 values instead of a single one. You can match on pretty much n number of values. You can match on lists and destructure them, all the fun stuff. So if player one's move is rock and the move from player 2 is scissors, we're going to return player 1 wins and pass in rock is through, scissors as beat, and we're going to assign that to the game result variable. Likewise, rock and paper, player 2 wins, paper and rock, player 1 wins, paper, scissors, player 2 wins, so on and so forth. So we get down to here, and we have these underscores. These are like kind of catch-all matches, I guess you would call them. It'd be similar as like using a default case in a switch statement in like Java or TypeScript. So here we know the only remaining patterns that we can match against are rock and rock, scissor and scissor, or paper and paper. So we're just gonna kind of treat them all in the same pattern match here, and we can return draw. And putting that all together, we match, assign it to game result, and then we can also, much like the beloved arrow or pipe in Elixir, we can pipe game result into game result to string, and then pipe the result of that into io.println. So yes, we have some types in pattern matching. What about first-class concurrency? Well, we can scale fearlessly with OTP, which is Open Telecom Platform. It is kind of the framework and primitives that power Erlang and Elixir's super powerful concurrency model. And we have that inherently because one of our compilation targets is to the beam. So let's look at what this looks like in practice. So again, let's focus in on this code block here. We're going to create a list using the list module's range function, and we're going to make a list ranging from 1 to 100,000. We're going to pipe the result of that into list.map, and then call task.async on each of the values. In fact, I actually have an error here. Not really an error, but we want to return I on the next line. Little typo here. So then we're just going to basically spin off 100,000 green threads concurrently, and the runtime is going to seamlessly handle that with ease. So we're also going to assign that to a task variable. We're then going to say let results equal list.map. We're going to pass it our tasks, and then we're going to pass this function from the task module called await forever. And what await forever is going to do is basically block on this line until all of the tasks have resolved from the async function above. And then finally, we're just going to print out all tasks completed. We're going to pipe results into int.sum, which takes a list of ints, and we're going to convert that into a string. Again, there should be a return I on this next line. So I also want to talk about the actor model and how Gleam implements it. How many Elixir devs are in here? Hands up. A couple of y'all. So Gleam implements OTP differently than Elixir and Erlang, primarily because it is, of the three, the only language that is a statically typed language. So let's look at what actors look like. So for the Elixir folks in the room, you can think of actors essentially as gen servers, right? And what a gen server is, kind of like generically, is a process that encapsulates some state or works over some state and allows other processes to communicate with it and interact with that state through message passing. So for our actor, let's say our state is going to be just a count, an integer, right? And then we're going to define a message that other processes can communicate to our actor with. So we're going to have increment. We're going to have a get count, which takes this thing called a subject. So this is also slightly different than what you might be used to in Elixir or Erlang. And put simply, what a subject is just a PID that has a type associated with it. Nothing more, nothing less. So we're saying our PID is going to be of a result that has a state, and then we're really never going to error here. It's just going to be nil. And then the final message is shut down. And you can also think of subjects and PIDs as kind of like mailboxes. Like one process can put data or a message into the mailbox, another process can read it out. That's effectively how PIDs work and subjects work. So then we want a way to actually get the count from our state. So we just declare a function, get count, we pass in our state, we pattern match on it to match on the only variant we have, which is count. We pull out the value and return that. So if you were to see what the get count function was inferred as, it would be a function that takes type state and returns type in. So the next bit is the handler. Essentially, the way that actors and gen servers work is they sit and they process messages serially, and this is kind of like our little event loop here, right? For processing each message that comes in, we get a copy of the current state and we get a copy of the message. So let's focus on the type, the return type here. This is actor.next that is going to return, or contains a message and state. So what does this actually look like in implementation? So if you were to dive into the actor module implementation, you would find this. So type next is generic over some message type and some state type, and it has two constructors. The continue constructor, which holds state, which is typically going to be our next state, and the selector thing, which isn't super important, but put briefly, a selector is a way to pull data out of a subject or a PID, and if you were to pass in the selector here as an option of some, you can kind of dynamically at runtime change how your actor processes messages and state, but that's, you know, beyond the scope of this talk. The other one is stop with an exit reason. So coming back here, let's start looking at our pattern match on message. So if we get an increment, we're going to say actor.continue, and we're going to return a new count where we get the current count of our state and we add 1 to it. And if you recall, we saw that there was a continue type as a constructor of the next function. So actor.continue, this function on the actor module looks exactly like this, and it's going to return this type. So if you were to see what this, like the type was inferred as here, we're returning a count with state, and for the selector, it's just a none because we're not updating the way we're processing messages. So next up is get count. We're going to take a mailbox. I like naming my subjects mailboxes in these contexts, helps with my mental model of it, but this is just a subject or a PID, and we're going to say process.send to the mailbox. So we're going to put a value into the mailbox, and that's going to be a OK state. And then we're going to go ahead and say, OK, actor, you can continue on with processing more messages. This allows us to communicate back and forth with other processes. So yeah, we'll get into that in a second. I got ahead of myself. And finally, the last one is shutdown, actor.stop. And there's a variety of exit reasons you can pass to an actor. And in this case, it's just processed at normal. We exited for a controlled or valid reason. So this is what it looks like to use. And we're also going to break this down line by line. So again, using let assert just for the ease of the example here. When we start our actor, it's going to spin up a green thread that is running concurrently with this parent process. And we're going to give it some initial state. Our count constructor was 0. And we're going to pass it a message handler, which is the function we looked at on the last slide. Now that actor is just going to be continuously running concurrently with the current process. Next, we're going to use the parent process to send messages to our child process. We're going to tell our child process to increment. So we're going to use the actor module send function. We're going to pass in our subject, our mailbox, to pass an increment message to that process. So we're going to increment twice. Next, we're going to use this function on the actor module called call. Again, we pass in our subject, and we pass in a message. We want to send it, and that final value is a timeout. So if we don't receive a response from our child process within a second, we're going to get an error value back rather than that OK state, which in this case, we really shouldn't be using assert here because it's going to panic and crash the parent process, which would be bad, but I digress. So we'll get out the state, and then we just print IO print line, current count, into string, get the count from the state, go on our happy way. Then we can, do the same thing again, increment again, and that should actually be 3 instead of 2. Typo on my part, but effectively the same thing. And then finally, we shut down our child process, and because this isn't our main function, our parent process will safely shut down as well. So we have first-class concurrency, and we get all the benefits of an actor module. We don't have to worry about mutexes and semaphores and rewrite locks and deadlocks and all these things. So what about DX as a core value? And what I really mean is from DX as a core value is like, don't make me think. Like, I want a language that's simple. And again, the experience you will generally get from Lua and Go. So Louis and the core team are incredibly diligent and thoughtful about keeping the language simple, small, and practical. In fact, there's not even an if statement in Gleam. Use pattern matching on a bool. So you'll match on some bool, and you'll match on true, and you'll match on false. And that's how you do it. That's how, opinionated the language is on keeping things simple, keeping minimal syntax, keeping one way to solve a problem. Like Go, you'll often find that there is one way of doing something, and you'll find that the language will naturally guide you there. And this is something I really appreciate about functional programming, is that languages that are functional in nature have a tendency to lead you to very simple and lightweight abstractions. Also, new features and syntax must meet a very high bar and strictly improve the language while maintaining its simplicity. If you were to join the Gleam Discord, you will commonly find people coming in and asking for things like traits from Rust, or type classes from Haskell, or functors from OCaml, or macros, and all these things. And without a good RFC and justification for it, the team will repeatedly shut these features down. So what about modern tooling? Well, Gleam is built on the back of Erlang, so we get all the benefits of mix and hex stocks. And the binary for Gleam includes everything. It includes the LSP server. It includes package management. You just do gleam.add package off of hex, you got it. Want to update your dependencies? Gleam update. Want to build? Gleam build. You want to publish your package? Literally just Gleam publish, and you're on hex. You want to generate documentation? Well, it's going right to hex stocks. It's just a really lovely tool to use. And like I was just talking about, it has stellar documentation because we get access to hex stocks. This is literally the result modules from the standard library on Gleam. Like, I think it's, the Gleam team is really, really good at writing documentation and keeping it simple. I will die on the hill that Gleam is without a doubt the best language to learn functional programming. 1, because it's so lightweight and simple, and 2, because they aren't using words like monads and all the crazy jargon that comes along with functional programming. Not that that stuff's not important, but it's not important to a beginner, and it's not important to get the utility out of functional programming. And what about helpful and friendly error messages? Well, the core team is essentially a group of Elm fans. So we have error messages just like Elm and Rust. So here are a couple examples. Error, unknown record field, user.alias. Did you mean name? The value being accessed here has this type. User, it has these fields, .name. Error, incorrect arity, which arity is just a fancy word for number of arguments to a function. Expected 2 arguments, got 3. The function on the right of the arrow here takes 2 arguments. All the arguments have already been supplied, so it cannot take the use callback function as a final argument. And finally, warning, redundant, list. You can remove this list wrapper. Instead of building a list and matching it, you can match on its contents directly. A case expression can take multiple subjects separated by commas like this, and it gives an example and a link to the docs. So we get DX as a core value. Now what about write once, run anywhere? Well, we have 2 compilation targets. We have the Beam and we have JavaScript. That pretty much covers the majority of the runtime environments I'm interested in, right? For long running processes and servers, I'm gonna compile to the Beam. If I wanna work in the browser, I'm gonna compile to JavaScript. If I wanna work in Edge and serverless, also gonna compile to JavaScript. If I wanna do CLI or dev tooling, I have the option of either language. So also, I like to think of Gleam as like kind of TypeScript ++, right? We can easily bind to and use all of our favorite NPM packages. And we also have the benefit of generating really solid TypeScript types in ES modules, which lets us use code we've written and compiled in Gleam in our other JavaScript or TypeScript. So we get all the benefits of JS and TS and its ecosystem without all of the pain points. So yes, we get write once, run anywhere. So is Gleam perfect? No. I'm one of those people that would love to see a macro system specifically. I was one of the people that was asking for a trait system, but I have found that the simplicity of the language and its constructs, like I don't miss it that much. But macros is one thing I dearly miss from Elixir and Rust. So I say it isn't perfect, but I do think it is ideal. It has all of the features that I listed out as my ideal programming language. So it is ideal, at least for me, and hopefully for you. I would encourage all of y'all to go join the Gleam Discord and take Gleam for a spin. And if you do, please hit me up on Twitter or anywhere you can find me. I want to hear about your experience. And if nothing else, if you haven't explored some of the concepts we talked about, like errors as values and functional programming, like step outside your comfort zone, try OCaml, step into Rust, learn more about lambda calculus and category theory. It's really going to fundamentally change how you think about problems. Thank you.